So the next talk is from Professor Jiji Zhang. Jiji Zhang is a professor from Hong Kong Baptist University, and Professor Zhang receives his PhD from CMU, and his previous work has appeared in both philosophy and computer science and statistics. So today he's going to give us a talk on two calculus and modularity in causal Markov categories. Let's welcome Professor Jiji Zhang.
Okay. Yeah, thank you very much for the introduction, and thanks to the organizers for this very great event, and also for giving me this opportunity. So I'm primarily a philosopher, so my talk will be more conceptual and abstract. Now, my main purpose today is actually to introduce something we've recently finished, but we're still working on extension of this. This is work trying to make causal reasoning more abstract, so that it potentially can be conceptually clearer and may also be applicable to non-probabilistic settings. So my focus today will be on this calculus known as calculus of interventions, or dual calculus, usually associated with Euler Pearl, but also with significant contributions from other people. I guess maybe dual calculus is not as popular in the audience here than in the community I'm more familiar with, but hopefully there will be few that may help me to see whether there's any insight gained in doing this. So the outline today, by the way, if you cannot hear me, please let me know by chat room, or it seems there's some instability in my connection here. Sorry about that. So I will first actually briefly introduce, oh, by the way, sorry, this work is a joint work with Yin, who is a mathematician. So during the talk, when you hear me say this can be made mathematically rigorous, you should have more confidence. Now, outlines that I will first outline a so-called categorical or category theoretic abstraction of the framework of causal-based networks. This is due to Brenda Fong in a work from a few years ago. And then I will basically make two main points today. One is about the dual calculus. I want to show that there is a more abstract and more purely causal calculus in this categorical framework that can be translated into a version of Pearl's dual calculus, which actually is simpler than Pearl's formulation. And then the second point is about this notion of modularity that has played an important role in both some philosophical theorization about causality and also some machine learning algorithms for discovering causal structures. Okay, so let me remind you of this framework called causal Bayesian network. So it's basically a causal interpretation, right, of the popular Bayesian network machinery. So if I have a set of random variables in this talk, you can just take all of them to be categorical, as Bayesian network machinery usually has it. And a causal Bayesian network over this set of variables is just a graphical model with a directed acyclic graph, a DAG, G over this set of variables, and also a collection of conditional probability functions, one for each variable conditional on its parents in that DAG. So the typical setup of Bayesian network. And it's called causal because it's supposed to entail a collection of post-intervention or interventional probability distributions. And the way the entailment goes is through this truncated factorization principle, which I will refer to as the intervention principle, sometimes also known as a manipulation theorem. So this principle just says that you consider any subset of V and you consider intervention on T. This I will just use Pearl's do operator to express. So given that intervene on T, the probability distribution of the rest of the variables will be can be calculated as this, is a so-called truncated factorization. You just take the rest of the variables that are not intervened upon, and is the conditional probability function multiplied. For example, if you have this very simple DAG, then you can calculate all kinds of interventional probability distributions. Now, there is a limit case is when you actually do a null intervention. So this is intervention on an empty set, which means it's a pre-intervention. And that, of course, just gives us the familiar factorization of the joint distribution in Bayesian network framework. And then by being a causal-based net, we can also talk about intervention on some variables. If you, for example, intervene on V2, then the rest of variables, the joint distribution of them, or the marginal distribution over the three variables after intervention will be factorized. This way, again, just each variable given parents. In this case, of course, it's an acyclic graph. There will be at least one variable that doesn't have any parent. In this case, it's just the unconditional probability function of this variable. Okay, now, two key ideas in this formulation of a causal Bayesian network are this. First one is that, in fact, each conditional probability function is taken to be encoding a causal module, a modular causal mechanism or process. And very importantly for my talk today, I think idea of composition is very important. The causal system is taken to be composed of these causal modules. And secondly, is that intervention basically just breaks the modules for those variables the intervention targets, but very importantly, does not affect the other modules. Right? Again, this is related to the notion of modularity, so that each module can be independently taken away. And this, of course, is why we have that truncated factorization formula for interventional probability distribution. Okay. Now, our point is that we can express these ideas more abstractly using the language of category theory, in mathematics known as abstract nonsense, but we'll try to make some sense of it. And this way, I want to show that we can more clearly actually separate causal reasoning from probabilistic reasoning, so gaining some conceptual clarity. Now, I don't think it will be fruitful for me to give an introduction to category theory here. If you already know it, my introduction will be redundant. If you don't already know it, I think a few minutes won't really get you through. So even though I wrote this whole slide to define category, all I want to emphasize really is this. In category, very important things are what they call morphisms, usually represented as this kind of arrow. You can think of this as a kind of abstraction of a function, right, from certain domain to a codomain. And in what we're going to do next, we're going to use this kind of morphism to abstractly represent a causal mechanism, a causal process. And very importantly for categories that it has composition. The morphisms are closed under composition, which means that if you have any two morphism where the codomain of the first morphism is just the domain of the second morphism, then you can form a composition of them. Now, for our purpose, okay, someone said missed my words. Sorry, is this going well, or should I actually restart my computer?
I'm okay here.
You're okay?
Yeah.
So, okay, and then I'm sorry to those cannot hear clearly. Okay, I'll continue. Now, composition here, right, in our framework actually will be representing causal processes running in sequence. So I'll ignore the detailed definition here, and I'll give you this. Okay, there's really something not working very well here.
Probably not your issue.
Not my issue. Okay, but then just now I had some problem moving my slides. Okay, it moves. Okay, so all through this talk, I'll try to make use of these so-called string diagrams. When my co-author first taught me this, yeah, I found them very annoying, but now I really love them. I thought they gave me a much better idea of a causal system than a DAG used to give me. Now, basically, we will use this kind of string diagram to represent morphisms. Again, in our framework will be causal processes or causal mechanism from some set of variables to other set of variables, very abstractly. So for example, here, this is a typical morphism, the second figure here, from some domain A to a codomain B. And again, all through this talk, it will be helpful to think of this as a kind of causal process abstractly described from some set of variables to some other set of variables. And then the composition, as you can see, right, can be visualized this way, very, again, simply just you have F, you have G. If the codomain of F or the output of F is the input to G, then you can get them together to signify a causal process running in sequence. Now, I just very quickly mentioned this notion of a functor. A functor is a generalization of a function and is supposed to be a transformation between categories. So when you have two categories, you can have a pair of mappings called F0, F1. F0 is to send the objects in the first category to objects in the second category, and F1 is to send the morphisms in the first category to the morphism in the second category. And then functor basically is just expected to preserve, right, the main elements of a category. So it preserves domains and codomains. So if you send a morphism, right, to the second category, to a target category, and then it will be a morphism actually with the domain to be F0A, with the codomain to be F0B, and similarly preserves composition and preserves identities. By the way, just in a category for each object, there is a special morphism called identity morphism. Okay, so that's not crucially important, but again, functor is really a transformation that preserves important structures between categories. So for our talk, this understanding is enough. And another kind of very important structure we will need here, this is also very popular and useful in category theory, is so-called monoidal structure. And here I give you a definition, but what's very important, this is a very specialized definition to make it simple, right? Define what's called a strict monoidal category. But in general, many monoidal categories are not strict, so definition will be more complicated. But for the purpose we have here, all you need to pay attention to is that in a monoidal category, you have additional structure given by so-called monoidal product, so that you can, each two objects, they can have a product, which is an object in the category as well. And any two morphisms, they have a product, right, in the category as well. Now, the reason why we need this in our current context is that monoidal structure is really good to represent causal processes running in parallel. So just now you remember, right? The basic category has this composition, which for our purpose is very handy for representing causal processes running in sequence. And then monoidal product actually gives you an expression of processes running in parallel like this. So we can visually represent, for example, the last figure here is two morphisms. They run in parallel. They form a product of F and G. Okay, now this is what Brenda Fang did, as I mentioned. So he defined an abstraction of a causal-based network, which he calls a causal theory. So this is a category, and the objects in this category, for our purpose, you just understand them as sets of variables. Actually, there are more than sets of variables in this category, but all we will care about in this talk will be sets of variables as objects. And very importantly, what are the morphisms in this causal theory? Now, as you can see, this is really trying to mirror the basic setup of a causal-based network. So most importantly, there's this basic mechanism or morphism. So for each node in V in the DAG, right, this causal theory is built given a DAG G. So it's a DAG-based category. And for each node in the DAG, for each vertex in the DAG, we have a morphism from its parents, the set of its parents, right, to this vertex. So again, this is abstraction, right, of those conditional probability functions in causal-based network. Here is more abstract, doesn't have to be probabilistic. It's just a causal process, a causal mechanism in whatever form from the set of parents to this node. So sometimes we call this a basic causal mechanism or causal process. And remember, right, some variables, some nodes in the DAG will have no parents. There will be root node, root vertices. In that case, of course, it's just this kappa for those variables will just be from the empty set, right, to this node. By the way, this will be a monoidal category. So this empty set is the so-called monoidal unit. And this, right, will be our most important basic morphisms in this category. And then in addition, we need two sort of auxiliary morphisms, which are also very important to express what we need. So for each node, we will have a so-called duplicate morphism. And this is needed to express the same variable entering multiple processes. Sometimes one variable actually participates in several processes, so we need to duplicate them to express that. And then there will be a discard morphism. Okay, so discard morphism is from this node to the monoidal unit, which is the empty set. This is needed to represent marginalization. Right? When you do marginalization in this framework, you basically throw away some variable or throw away the information of some variable, as Fang put it. So our so-called causal theory, again, I won't bore you with the detailed formal definition because that will take us too much time. But the basic idea is that from these basic morphisms, this is so-called generators. We can generate a so-called free category, right, by just taking compositions and the monoidal products of these morphisms. Subject only to the axioms, a few axioms. Again, I won't show you those axioms because it's too much for today's talk. And I'll just let you know that those axioms are actually recently formally given in a definition of a so-called Markov category. A Markov category is the abstraction of category of probability measures. So those axioms are closely related to some properties of probability measures. And for our purpose today, right, we need to just understand there are these basic morphisms, especially the basic mechanism from parents to child that will compose more causal processes and morphisms in this category. Now, if we have that, then we can define in this category, we can actually construct a kind of morphism which is the central object of our interest. This is, so I would denote this kind of morphism with this notation here. So for any set of nodes T and W, So there's a morphism we can write from T to W. So this double bar is actually intended to remind you, for those who know Pearl's work, right? Remind you that this T here is intended to be an intervention on T, right? That's the intuitive meaning. So we intervene on T, we see the effect on W. So this actually in this framework will be a morphism from T to W. And if you want some intuition, you can always think of this as an abstraction of the probability of W given due T, right? The post-intervention probability of W given that T is intervened. But this is abstraction, so it doesn't, in itself, doesn't have any probability. It can be interpreted as a probability. It can also be interpreted in other ways. And this morphism, which we will refer to as the causal effect morphism. So again, I'll get rid of definitions because that's too complicated for our purpose today. But the idea is intuitively very clear. For example, just give you an example. If you have a deck here, and if you wonder what's the causal effect morphism from the node B, or you may say from a variable B, to the two variables D and E. So whenever I just write two variables together, I mean them together, joint, right? Or if it's two sets, right? It's a union of them. So the idea is really just like the intervention idea in the context of causal-based network, right? When you actually intervene on B, you actually will, of course, cut the arrow from A to B. So you will not consider any directed path into B anymore. Since the target is D and E, so basically you just look at all the directed path that will go to either D or E, but not through B. You can start from B, but cannot go through B because any arrow into B is supposed to be cut, right, by intervention. So you consider those directed path to D and E not going through B, then along the way, you will go through a bunch of nodes or variables, and then you just compose those basic mechanisms together to get this big mechanism. For example, in this case, if you consider B to DE, then you can see that here, right, starting from B, you will go through C and D and go through C and E. And also, you also have a directed path, right, from A to C to D to E. So basically, the variables that will matter in this causal process from B to DE will be A, B, C, D, E. And that's how you actually compose this morphism here, this process. Because you will start with A, right? A is the root, and it's just the kappa A. Kappa A is from the exogenous context, you may say, from the empty set to A. There is a causal process. It's an exogenous process. And then this A and the B, that here is B, right, will feed into the kappa of C, right? Because C has the parents A and B, so it has a basic causal mechanism from A, B to C. And then once you get C, we duplicate. So this is a duplicate because C will enter two processes. C has two children here. Right? C has a child E and has a child D. So you will enter the process for D, it will also enter the process for E. So after you duplicate, one of them is sent to the process for D, and the other of them is sent to the process for E. And then here, once you generate D here, this D will also be duplicated. So this is a duplication again, because one of the D is just your output, right? Because suppose your output is D and E. So one of them is going to output. The other, on the other hand, since D has this child E, right? D is actually participating in the process for E. So it will feed into this kappa. As you can see, right? So this part of the system, right, from B to DE is again just composed in some way with the help of duplication of these basic mechanisms. So the key idea is that, right, the DAG-based causal model, especially causal-based network, the key idea really is the causal effect, the causal process, no matter it's from which variable to other variables, they're actually in the end all composed of the basic causal mechanisms in some way through with the help of duplicate and discard if needed. Okay, so that's the setup of this work. And now I'm going to tell you some results we had. And I thought if you are familiar with do calculus, this result might be of interest. So I have 3 minutes. Is that right? Or sorry?
Yes, theoretically.
Oh, okay. Let me see. Actually, how about let me go to show you our main result. Basically, for these causal effect mechanisms, we can define some significant notions. So here is one notion, is that a causal effect sometimes may be so-called decomposable over a variable. So just look at this figure. What this figure means is that the causal effect or the causal process from T to UW can actually be decomposed in this way. This means that you first just take the marginal of this process just from T to U. So you first generate U from T, and then together with T and U, you generate W. So the whole process from T to UW can just be composed or decomposed in this way. Now this doesn't always hold, right? This requires conditions. But whenever this holds, right, you can see that this is a kind of in probabilities models is kind of chain rule for interventional probabilities, right? The chain rule is that the probability of U and W given do T is actually the probability of U given do T times the probability of W given do U and do T, right? So all these bar denote some kind of intervention if you talk about probability models. But here is a more abstract description, right? It's just saying that this whole process can be decomposed. Now, what's the condition for this? It doesn't always decompose this way. Now, the condition of this is actually quite simple, is the so-called track separation. For those of you who are familiar with graphical models, right? In DAG models, of course, we always talk about D separation. Now, track separation is a simple notion. First of all, tracks are just those paths that do not contain any so-called collider or colliding path. Right? Those things we don't care about here. So track basically is either directed path or is a disjoint union of two directed paths joined together. Now, the forward track just means that, so a forward track from a variable I to a variable J is just a direct path from I to J. But the backward, right? Think of backdoor if you are familiar with Peirce's notion. A backward track is actually a track between I and J that's into I. Okay, forward track from I to J is a track out of I. Backward track is into I. And then forward T separation is basically saying that, right, all the forward tracks are blocked. So X is forward T separated from Y by Z, just means that every forward track is blocked. And backward T separation is the same thing. And T separation just means that it's both backward T separated and forward T separated. So give me 2 minutes, let me actually at least finish do calculus. So we can prove just in this very abstract setting that a causal process like this, right, from T to UW is decomposable over U, just in case, if and only if in this category, that U is backward T separated from W by T. Okay, for those of you who are familiar with Peirce's do calculus, right, you can already see some affinity with the second rule of the do calculus. Right, it's a kind of backdoor rule. The backdoor track will be needs to be blocked in order for this to be decomposable. And then we can define two more significant notions other than decomposability. One is just causally screened off. And this one just says that if you have a process from U and T together to W, and whenever you actually can be factorized in this way, namely you can throw away U. So this just means when you write this, it means you discard U. This is the discard mechanism, right? The morphism. So you can throw away U and just consider from T to W. So in this sense, we will say U is causally screened off from W by T. And then another notion is U and W are causally independent given T. And by this, we just mean that given T, from T to UW, this process can be, again, factorized into two marginals, right? Can be you may say, a product of the marginal from T to U and the marginal from T to W. So the joint effect can be factorized into two marginals. Okay, and then we can show that causally screen off is actually just corresponding to forward T separation, and condition independence corresponds to T separation. So in the end, we actually get a so-called generic dual calculus. This actually matches Pearl's 3 rules of dual calculus, but first of all, in an abstract way. So it doesn't concern probabilities. It's actually formulated rigorously in the language of category theory. Again, it can be made rigorous. I didn't give you all the technical details. So this kind of calculus, they applies to all causal models based on this deck, not just probabilistic models. But probabilistic models is one very popular salient model, but there are other options as well. For all of them, our dual calculus apply. And in particular, if you go to probabilistic models, you will recover a specialized version of dual calculus. Specialized version is just given here. Namely, you can have the first rule saying if U and W are T separated by T, then you can do this so-called deletion or insertion of observation. So this is what Pearl calls, I can insert or delete an observation when this happens. And the second rule is the backward T separation rule, says that, right, you can actually have this chain rule of dual probabilities, and which is just equivalent to Pearl's second equation, a special case of that. And then third, you have similarly a special case of Pearl's rule. Now this specialized version, so maybe I just finish with this. Sorry for the delay. I think already 3 minutes past. For those of you who are familiar with Pearl's dual calculus, you can see that our version actually is much simpler and is actually a special case. It's a special case in the sense that in Pearl's version, there is a common conditioning set that's actually taken to be empty in our version. So we're sort of just use a special case of Pearl's dual calculus. However, so I didn't realize this before, but now given this work, I suddenly realized there's a very simple argument showing that the specialized version is in fact equivalent to Pearl's full version, given the probability calculus. Actually, I'm asking around whether this is already known in the literature because the argument is quite simple. But my point here today is that we now have this simpler but equally strong dual calculus. And this is actually image of the generic calculus we derived in the abstract causal category. So in that sense, it's actually the purely causal component of the standard dual calculus. So the standard dual calculus sort of mix causal reasoning and probabilistic reasoning. And when we do this, we actually tease out the purely causal part, and the rest is probability reasoning. And then we can extend this to actually talk about modularity, which is a very important notion these days in some causal discovery approach. But for the interest of time, I will skip this. I'll just let you know that our framework actually gives you a quite novel characterization of what modularity really is. Again, it's in terms of some kind of composition of causal mechanisms. So you can talk about when two causal mechanisms are independent or modular. And we can give a graphical characterization of that as well. So to summarize, this is very abstract, but I know, yeah, I don't know how applicable it will be to data analysis at some point. But I do hope that our work on this modularity will have applications in causal discovery soon. But just want to say that in the list, when you actually study this abstractly, you gain some new insight of the dual calculus. At least I did. I didn't realize, for example, the simpler version is actually as strong as the full version. So let me stop here. Sorry for the extra time. Thank you very much.
Okay, thank you for the talk. So because of time, so we will leave no questions and discussions.
Okay, thank you.
People have questions, we can discuss in the chat.